And it's my distinct pleasure today to introduce my colleague and friend, Professor Ramona Voght. She's a staff physicist at Lawrence Livermore National Lab in the Nuclear and Chemical Sciences Division and an adjunct professor of physics at UC Davis. She is a fellow of the American Physical Society and currently secretary and treasurer of the topical group on hydrodynamic physics and the division of nuclear physics. She's also a member of the APS Committee on Fellowship. Her interests in physics include both high energy nuclear physics and the physics of nuclear fission that she will be talking about today. She's also an APS Outstanding Referee and on the editorial board of Physical Review Research. So please join me in welcoming Professor Voght. And the floor is yours, Ramona.
Okay, so thank you very much. It's my pleasure to be back here, if virtually at least, to talk about an exciting topic, nuclear fission in the cosmos and on Earth. So let's see, changing those slides, that's great. So what is fission? So to me, you heard about some aspects of nuclear fission already. Oh, should I start my video, by the way? Would you like to see me, actually?
Hey, Ramona, it's totally up to you if you would like to.
It's it's fine. I didn't realize it wasn't on. Okay. Um, so so nuclear fission is the epitome of the conversion of mass to energy, and you heard about this already earlier in the week from my colleague Jörn Randrup. And basically, as he described, it's the heavy nucleus splitting in two, and when it actually splits, that's called fission, and it releases a large amount of energy when it does. And this is not exactly changing lead into gold like the ancient alchemists wanted to do, but it is a form of nuclear transmutation. So you change this one element, like uranium or plutonium, into two fragments that then emit neutrons and photons. And it was discovered by Hahn and Strassmann, among others, but not everyone understood what it was. It was only when Meitner and Frisch um, explained that it was actually the nucleus splitting instead of making a larger element, and they called it fission, in analogy to the cellular fission in biology, where a cell splits into two. And it's a really great laboratory for studying nuclear physics with a mix of dynamics and structure. Okay, all right. Here we go. So fission was discovered more than 80 years ago, and you might think that after all this time we know everything about it, but that's really not true. There's still a lot left to know and to learn. The previous measurements that have been made could really be improved, and a lot of the models were very simplistic and were made for a time when computers were very large and very slow. They didn't process a whole lot of information at a time. So things have evolved a lot since then, and the last few years have seen a renaissance in fission studies. For example, from Sarah's group at the University of Michigan and other places. Um, and a lot of the new measurements are challenging these old results, and making them better, reducing the uncertainties. And there are large scale computing is now available, and that means that fission can be studied more as a quantum mechanical many body problem, and a true theoretical model of fission may be possible. I mean, there are people who are doing it and say that they're doing it right, but there's still a long way to go to make it really, say, fast and user friendly, and to be used in models like the ones I'm going to be talking about. Um, so there's a need for phenomenological models to fill the gaps in the data and the gaps in our knowledge and understanding. And judging by the number of people listening in, there are a lot of young people that are entering the field, and there's a lot of areas of interest that they can pursue. Um, and when I mentioned in the cosmos, I'm going to explain a little bit about this in the next part of my talk, but the abundances of elements in the universe can be explained in part by what's known as fission recycling. Um, and people have been looking at the anomalies in neutrino spectra from detectors that are situated near nuclear reactors. And this is like the reactor anti-neutrino problem, it's called. And these anomalies can be resolved partly by studying fission product yields. And I'll explain what those are too. So, um, so fission can explain a lot about the um, abundance of heavy elements in the universe. Um, Now, if you think about it, what you know about our sun, right? Our sun is shining because there are nuclear reactions going on, and they're actually producing very light elements. The solar neutrino process um, is making elements up to, say, a boron or beryllium, maybe. But as time goes on, the star makes heavier and heavier elements in the interior, but it can only go as high as iron because that's stable. And then when the stars are out of fuel, they can't burn anything more, say with an iron core, then they collapse or explode. And in an explosive stellar process, or in neutron star black hole mergers, that are detected in these gravitational wave observatories that you've heard about, you can make heavier and heavier elements through a process called rapid nucleosynthesis, or the R process. And eventually these nuclei get so big and very neutron rich, so there are too many neutrons, and the nucleus fissions and produces two lighter nuclei that can start the process over again, and that's known as fission recycling. So that's in the cosmos, but what can we learn about fission here on Earth? Well, I'm sure you've heard about new elements that have been discovered in the last decade or so, and this periodic table of the elements is still growing as we learn to make heavier elements in the laboratory, because many of these the heaviest elements that have been produced don't exist alone in nature. There are a few, but you can't go and dig for them and take them out of the earth and put them in your detector. It's not that easy. We talk about making super heavy elements, and these are very short-lived and decay quickly until the decay chain ends with fission. And people who are trying to produce these super heavy elements, they're looking for something called the island of stability, where new elements will be long-lived. But so one drawback of that is if they're really stable, then they're going to be a lot harder to detect, because they'll exist a lot longer before they decay, so it'll be harder to determine that you've actually made a new element, as I'll explain. And as you know, because fission releases a lot of energy, it can be used to generate power, and nuclear reactors are making use of this energy release to generate electricity. But you don't actually need a reactor. I mean, if you Google this address here about the natural nuclear fission reactor, there are natural nuclear reactors made where uranium deposits in the earth got flooded with groundwater. So I mean, it's actually a nice example of an out of not exactly out of control situation, because it didn't explode, but you had it just continued using up this fuel and until it was all used up. And you can if you Google that, you'll find out about it. Okay. So where are the elements that fission on the periodic table? These are the actinides, and uranium, plutonium, californium are elements you've heard about a lot. Californium that spontaneously fissions, californium-252, and then uranium and plutonium are often used as fuel, And then these other actinides, they also fission, and as well as these here on this last line in black on the periodic table, these last four, uh, fluorovium through oganesson, um, are the heaviest ones that have been most recently discovered. And um, so, so that's one way of looking at the elements. This is another. This is the chart of the nucleides. So proton number is along here. So each step in Z on this on the y-axis here um, represents an element in the periodic table. So each step up from goes hydrogen, helium, lithium, and so on is represented by each line here, and each horizontal line for a single element shows. So for a given Z, the horizontal direction shows how many isotopes for that element exist. So it's the same element but different numbers of neutrons, and some are more stable than others. And the black ones here are stable isotopes, and the actinide region is way up here. So have we gotten to the island of stability yet? We may have reached it in some of these things like neutron star mergers, but it's harder to detect in the lab because what we really need is very heavy neutron-rich targets and high-intensity neutron-rich beams so that we can produce high Z and high N elements. And as I already mentioned, these long-lived elements may have long enough lifetimes that counting them can be hard, because what they do is they detect fission as the last step in the process, but you have a decay chain that you can detect they say alphas that are emitted, or in some cases other types of radiation. Now this is production of element 117, that's tennessine, and it was named tennessine because the 249 berkelium target was made at Oak Ridge, and this target was bombarded by a calcium 48 beam. Now calcium, the average mass of calcium is typically around 40, so this is very neutron rich, 8 more neutrons than usual. And so this is one of the best beams that you can use, but berkelium or californium, say, are two of the targets that, I mean, basically two elements that can still be made into targets back up here. You're not going to make, say, a target of nobelium or lawrencium or something like that very easily. So you need heavier, stable targets, or which are not going to be very easy to do, or very heavier, intense beams than calcium 48 to discover these higher Z elements. And it's kind of interesting. Oganesson was discovered only with 2 events, and tennessine with 6 total events. So it's just very delicate to be able to manage to see these different isotopes and recognize them at the time. Now, oganesson, like I said, is with 118. It should be fairly stable, and its placement on the periodic table shows that it should be a noble gas. So it'd be interesting to see how and when we get to 119. Okay. Now, how are these elements made in the cosmos? Like I already mentioned, we look at stars like supernova when a star collapse, the neutron-star merger, and then once these events happen, then we look at stellar nucleosynthesis. And so one thing you might notice here is the chart of the nucleides is not such that equal numbers of protons and neutrons are typical. They can start out that way when for, say, light nuclei, but then they start the chart starts to bend over, and that's because nuclei that stay together generally have to have more neutrons than protons, because if you put too many charges together without some neutrons to separate them, then then um, the charge starts to, the electromagnetic force starts to overwhelm the nuclear force, and the nucleus can't bind anymore. So, so that's why the chart bends over like this. And the periodic table is designed to sort of highlight where there are closed electronic shells. Well, these horizontal and vertical lines here that are outlined, these represent closed nuclear shells. And so, it's at some cases, like 10, 132, where Z equals 50 and N equals 82, you'll have a fairly stable nucleus, as opposed to, um, or lead is another case. This is lead right here. It's very stable. It has a number of stable isotopes. So when you're at a closed nuclear shell, then you tend to have more stable isotopes. So this is an idea of how the R process actually works. It builds up heavy elements, and there are some hang-ups at these closed shells where it sort of decays back down a little bit and goes to greater numbers of protons along those vertical bars here. But mostly you're in this area that's very neutron rich, way out here, away from the observed table chart of the nuclides. And when the nucleus gets too neutron heavy, instead of just emitting a single neutron every time, it will just fission. And these fragments can start participating in the R process all over again. So when the products go is down here, say a heavy fragment tends to have Na of about 140, and the light fragment around 90 or 110 or so, depending on what the nucleus is at fissions. So this is kind of an example of how a nuclear fission event works. I mean, you can have different projectiles coming in, or you can have spontaneous fission, and you form a compound nucleus. And in the case of spontaneous fission, it's just the original nucleus. But the shape evolves, and I'm sure Jörn told you a lot about that earlier this week. And then you get toward decision, where the neck snaps, and then you're left with these hot and excited primary fragments. And typically one is heavier than the other. That's why there's an H and L there for the heavy and the light. And they're hot and they're rotating, and so they want to get rid of their energy, that extra energy, in the most efficient way possible. And that's actually by first emitting neutrons and then photons. And neutron emission goes by the strong force, photon emission by the electromagnetic force, and after that prompt emission, you're left with prompt products, or you go from fission fragments to fission products. And then after a longer time, there are delayed processes that go on. Beta delay, that means that you emit electrons and antineutrinos. You can also have delayed photon emission and neutron emission. And that's like an inverse beta decay would emit a neutron, and a normal beta decay, a neutron changes to a proton. So you're left with cumulative products after a longer time. And these beta delay processes go by electromagnetic and weak forces. So you have like all forces of nature except gravity involved in fission. So you can have a couple of different things go on. You can do controlled nuclear fission for power, where you have a nucleus, one of the neutrons that's emitted. There's typically at least 2 neutrons emitted in fission. And in a reactor, you want criticality to be 1. You don't want it to be out of control. So that's why you have these, the control that absorb some of the neutrons. So you have an exactly critical system. It doesn't blow up like an uncontrolled nuclear chain reaction where each neutron can go off and make more fissions until it just explodes. Um, so that's really the difference between controlled and uncontrolled reactions. But so okay, I've talked about I think all of this already. But what do how do you actually like calculate these processes? How do you model it, and then how do you understand data that comes out of these new experiments that have been going on? So to really do that, you need a model that's better than the average fission model. And the average fission model, say 15 years ago or so, was a black box where the neutron and photon energies were sampled from the same average distribution. Like here, you just see no matter what the kinetic energy of the neutron that was emitted in the model, and just sample from that same distribution the next time again, regardless of how many neutrons were carried away. So you knew nothing about energy and momentum conservation, and you didn't have any way to address any fluctuations or correlations. But the detailed or more discrete fission model will give you all of the kinematic and particle correlations, and that's the kind of model that I've been involved with Aaron on making a detailed fission model, and it keeps track of the neutrons, photons, and fission products in each individual event, and so you have automatically included correlations and energy and momentum conservation. And like I was alluding to, you need specialized physics models to study fission like this, and we've been developing FRIA, fission reaction event yield algorithm, since 2009 to study fission event by event. And basically, we borrowed this heavy event by event modeling from high energy physics, where models like a code called Pythia were used to have been or still being used to model potential signals, and also to be used in detector development. So you know that if you are going to produce this particular process, will it be seen in your detector, for example? And FRIA generates a lot of events very fast and keeps track of the fragments, neutrons, and photons. And it was the first fission model that's been published and made generally available. And it's basically show the importance of energy and momentum conservation. And it's fast enough for users to study a lot of different events and with just with your laptop. And this is a big advantage. There are other codes that have been put out. CGMF is about to appear in computer physics communication, like FRIA has been already in 2015 with the first publication. In 2018 was the revised version, upgraded. Fifferland from France, and GEF is a code from Germany and France that you can find a big paper on in nuclear data sheets. And before these codes, most others were deterministic, meaning that they only addressed average events. So you just use a couple of parameters with an average fission model, and it was basically to have some good understanding of the prompt fission neutron spectrum, like I showed on a previous slide, on this slide. So this is a prompt fission neutron spectrum. Okay, so now let's step through a fission event and see what happens before fission, how the energy gets partitioned between the fragments, and how did the fragments get rid of their excess energy. I mean, I showed this diagram a few slides back, but we can learn, we can know more about some of the details. So Now, the before fission actually occurs, where that neck snaps and you have two separated fragments, neutrons can already be emitted in induced fission. This doesn't happen in spontaneous fission. So if you have a high enough energy neutron coming in, the compound nucleus that's created with the neutron plus, or incident particle plus the target, it may be excited enough to emit neutrons before the fission happens. And I mean, sometimes if a neutron gets emitted, it takes up so much energy that the nucleus can't fission anymore. But generally, it's quite possible that the fission can still happen. Say, for example, the pre-equilibrium neutron emission. So the incoming neutron doesn't quite equilibrate with the nucleus, but instead it just gets spit out again. So it's the same neutron that goes out um, in general when there's only one neutron emitted. So there's a specific endpoint energy for that process, which is basically the difference between the incident neutron energy and the neutron separation energy. And on the other hand, there's multi-chance fission, where the neutron actually becomes equilibrated with the target, and it still is energetic enough that it spits out additional neutrons. So I mean, this is the general path where there's no neutron emitted. This is called first chance fission, and at some point, you can have a neutron that one neutron that gets emitted, and then there's still enough energy to go on to fission, and that's called second chance. Um, and there are cases where these chances can have thresholds, right? Because you need to have enough energy coming in to be able to emit those neutrons. So it has to be higher than the neutron separation energy in general. So the second chance fission threshold is generally about 6 MeV or so, and this is around 12 and 18 and so on and so on. But so then it's possible that you can emit one neutron and there's still enough energy left to emit a second neutron and then still go on to fission, and that's third chance fission and so on. But then it proceeds to fission, and then after fission in codes like Freya, the fission fragment characteristics are sampled. So these are the fission fragment yields. And I plotted here a bunch of different plutonium isotopes together. They differ by, say, several neutrons, so it's really hard to see any big difference on this kind of scale. But there's always one, say, a peak here at about 100, mass of 130, 135, 140 around here. And then, say, lighter elements would have this light peak moved to the left. Heavier ones would have a narrower separation region between the two peaks, for example. And there's typically a dip in the middle, and then a fairly steep drop on the wings on the side. And as you go up in energy from thermal neutrons to, say, a few MeV to, say, 14 MeV or higher, then these edges start increasing the yields, and it gets broader. And also this dip tends to fill in, and you could get as far as having symmetric fission here for high enough energies. Okay, so those are the fragment yields. You also have to worry about the fragment charge. And we also use the measured total kinetic energy generally to sample from. And these are a bunch of neutron-induced fission measurements and a couple of spontaneous fission measurements. And they all tend to have a peak at around 130 or so, where you have a closed nuclear shell. And so there the nucleus is fairly stable and isn't going to emit many neutrons. And so the kinetic energy of the two fragments moving apart is going to be much, the dominant thing. So once you've identified the mass and charge of one fragment, you automatically get the mass and charge of the other fragment by mass and charge conservation. And once you know their identities, you know their masses, you can determine the fission Q value, and you take the difference between the Q value and the total kinetic energy, and what's left over is the total excitation energy, and then from that we split that between the two fragments and de-excite them. Okay, so this total excitation energy, TXE, gets partitioned between the two fragments, and in our case with Freya, we make more of an empirical split between the intrinsic or statistical excitation, which is going to do most of the neutron emission, and the rotational energies, which really tells you about the fragment spin, and then also photon emission. And this energy partition here of the excitation energy in particular is probably the hardest to get right because there's not a lot of data. You're basically relying on the neutron multiplicities as a function of fragment mass and total kinetic energy, and also on something like that. There's similar measurements for photons, and a lot of those photon measurements aren't terribly accurate, as I'll show you. So and most of those measurements are for spontaneous fission or thermal neutrons, and so higher energy neutrons, it's much harder to do these measurements, and you're trying to measure everything at once, and that's not very easy. You need a good fragment detector. You need both a detector that will do neutron photon separation, and you need enough of them that you might also like to learn something about the direction, which I'll tell you about in another few slides. But there's not much data on the energy dependence of these, so you have to sort of make some guesses about that. And I mean, if you have multiple detectors for neutrons and photons, that will, like I said, you provide some directional information, and that can tell you a lot more about correlations, not just in bulk, say, like with neutrons with the fragments or photons with the fragments, but also neutron correlations with each other or with a fragment, and so on. So in this excitation energy, this is the total excitation energy here. It gets split into say a rotational energy and a statistical excitation, and you can divide these up separately between the two. And our code Freya is designed so that we do both linear and angular momentum accurately with conservation laws followed all the time throughout the process. Now we de-excite the fission fragments by, like I said, we first reduce the intrinsic excitation energy by neutron emission. This doesn't actually change the spin very much, and this is on the strong interaction time scale, so a few femtoseconds after the fission, the neutrons are gone. The photons can pretty much typically reach the detector first because even though they start later, they're faster because they travel with the speed of light. But generally, photon emission is assumed to begin more or less after no more neutrons can be emitted, and this reduces both the excitation energy and the angular momentum, and this is going on an electromagnetic time scale, like I mentioned. And then when we do the beta decays that can emit electrons and neutrinos, and like I already mentioned, fission is pretty unique this way because gravity is the only force of nature that doesn't really play a role in fission. So evaporate neutrons from the rotating fragments and do that first. For each known mother nucleus, we add the ground state energy to the excitation energy, and we can calculate the Q value, and that we have to know also the neutron separation energy, and so we have a range of energies that are possible um, to emit a neutron, and that's going to change with each neutron emission, because then you have a new nucleus, same element but different mass, and probably also with a different separation energy. And we use a Weizskopf-Ewing neutron emission spectrum, um, and the maximum temperature is based on the maximum excitation energy and the nuclear level density. Um, so we do that, but we also take into account that with the fragment is rotating, even though it's not rotating that. I mean, it is rotating, so we have emission from the moving surface, and we have to boost the velocity gets boosted, and once the neutron is emitted, the nucleus absorbs this recoil, linear, and angular momentum. And we've done a lot of studies of this, and we've shown that it's actually not that much, but it's still, if you're conserving energy and linear and angular momentum, it's still important to keep that take that into account. So once you start photon emission, typically the excitation energy is very close to the neutron separation energy, and then you get rid of that additional remaining excitation energy by sequential photon emission. And first, you can still be fairly high up, and you're not, you're basically emitting continuum photons, where we're taking into account that most of them are going by the giant dipole resonance, and then once you come down to what's called the ERAS line, this is the ERAS means dizziest, so the highest spin, and then these transition, you can you do these emissions of quadrupole photons, and then you can reach say discrete levels where you use the ripple decay tables to determine where the transitions are, and so then you get down to the ground state where the fragments aren't excited anymore, or at least not excited enough to do more emission until later in time, like through the beta decays or delayed photon emission. So, like I've already discussed, fission results in correlated observables, and in the laboratory, to learn about fission, we can study one event at a time. Say californium is a really good source because it spontaneously fissions a lot, and so you can have really good statistics. So it's really studied quite a lot, and other spontaneously fissioning nuclei not so much, because you have to sit and count longer, and so your statistics aren't usually as good. But I mean, because of conservation laws, like I've been saying over and over, every part of the fission event is correlated, and thus you really want a complete event, complete event of calculation. Sorry about that. Anyway, so the correlations between neutrons and fragments are on a sort of in bulk basis are shown here in this plot, for plutonium, uranium, and californium. It's not. I should have remade this plot one of these years, because it's not really quite in order, because uranium is Z of 92, plutonium is Z of 94, and californium Z of 98. So I'm sort of jumping around a little bit here. But these are different data sets. Some come with statistical uncertainties, some don't. The bars here on the Nishio data are basically the full width half max, that it's sort of indicating where, for different Z's you might get emission. So this is the neutron multiplicity as a function of the fragment mass, and you see what's called a sawtooth pattern, and this tooth is sharper for larger masses, so it's kind of not very sharp for uranium. It's a little sharper for plutonium, and it's quite sharp for californium, because that dip in the in neutron emission, where the nucleus is most stable and you have the highest total kinetic energy, is always at the same point, around a mass of 130 or so. And if this is tin 132, this is a doubly closed shell, but at least it's N of 82, so it's harder to excite, and the number of neutrons that are emitted is small compared to, say, a nucleus that may be more deformed or more excited. And so that's where the sawtooth pattern comes from. It has something to do with the nuclear structure, and I'm sure everyone talked about that on Wednesday. And you can compare neutron to photon emission as a function of mass. And here's these data sets compared to a measurement by Nardi from the 70s. And maybe it has a sawtooth pattern, maybe not. And there's some shift here between the two, but it seems a little less dependent on fragment mass than say the neutron emission. But it's also, say, more difficult because you don't always get consistent numbers of depending on how the measurement is done, you probably won't get as good a mass resolution already for the photons than you do for the neutrons. And also here, okay, I've divided this is the energy of the photon, not the multiplicity, and I've divided by here 1.75 MeV to put it on a similar scale with the californium data, and I've done the same here for the photon energy and multiplicity, but by a factor of 2.5 instead of 1.75. And okay, there are more neutrons emitted from californium, but also somewhat more photons as well. The average neutron multiplicity for californium is about 3.76, whereas for uranium-235 thermal neutrons, it's about 2.38 or so. And then you also have smaller numbers of photons emitted. And here, over here, I said this was the range in Z that's possible for a neutron emission for that A. These are uncertainties, and they're very large. So they're suggestive, but it's not really possible to draw much of a conclusion from the large uncertainties on these data points. Okay, so you can also look at neutron angular correlations, like I mentioned, and I showed two examples here, just calculation. So you can have a neutron correlated with another quantity over here. It could be another neutron, or it could be, say, a light fragment. In the case of neutrons, you can have, this is a neutron-neutron angular correlation, and when you take all neutrons, any two neutrons together, and you're not worried about which fragment they come from, then you get this pattern with the open circles. Um, Now, a lot of cases, neutrons are coming from, say one neutron is typically emitted from each fragment, or say at least one neutron. And sometimes you can have, multiple neutrons um, from a given fragment. I mean, with californium, you have a nearly four neutrons emitted, so you can, each fragment is going to emit close to two, and so you can have correlations each from say each fragment. They're moving apart from each other, and so in the rest frame of the fragment, the neutrons are basically emitted isotropically, but yeah, in the lab frame, they're boosted, so the neutrons are always going to be moving basically in the direction of the fragment that emitted them, and how much that is depends on whether they were emitted on one side of the fragment or another, more or less. Um, so so when each of the two neutrons that are used to form the correlation come, from different fragments, then it's back to back, and you have a this peak at 180 degrees. But if they both come from the same same fragment, then they're going to have a peak at 0 degrees. And if they're both coming from the light fragment, then the light fragment typically has a higher velocity for momentum conservation because it's lighter mass. And so you'll have a higher peak over here relative to both neutrons coming from the light fragment. Sorry, from the heavy fragment. When you put them all together, then weighted properly, then you get this kind of emission pattern with a peak at 0, a peak at 180 degrees, and a dip in the middle around 90. When you have correlations between the neutron and, say, the light fragment, then, of course, if the neutron comes from the light fragment, it's going to be traveling in the same direction. And so you'll have a strong peak towards 0 degrees and nothing at all, basically, at 180. And if the neutron comes from the heavy fragment, then it's, of course, going to be going in the opposite direction. And so you'll have this peak at 180 and nothing at 0. And then altogether, taking neutrons from both fragments reduces that strong peak near 0, so it's moved a little bit to the left, and the peak at 180 is moved down, so it's stronger at 0 than at 180. But this is a typical distribution of these neutron heavy fragment correlations. And I should mention that these also depend on I already mentioned on the average neutron multiplicity. Like, for example, if you have, say, a nucleus like plutonium-240, where the average from spontaneous fission, the average neutron multiplicity is just a little bit more than 2. So the peak at 180 is probably going to be somewhat bigger. The peak is going to be emphasized a bit more. And it also is going to depend on the neutron energy. So, and I could talk a little more about that, but say lower energy neutrons are going to be, say, closer to the fragment themselves, whereas higher energy neutrons are more outward directed and also more rare, so the peak can get higher too. So you can see that here. This is different neutron correlations with different threshold energies. So these are, the black dots are all neutrons with energies greater than 0.425 MeV, going up to all neutrons with energies greater than 1.6 MeV. And you can see that the distributions go from somewhat more isotropic to more peaked at 0 to 180 degrees. And that was for californium. This is also for californium, but it's neutron light fragment correlations. And you can see that the strength of the correlation, say at 0 degrees, is going up as you go from light fragment masses of 91 to 106 as you get, so that's as you get closer, um, say you're going from say here to here, so you're moving closer to the to the peak of the neutron emission on the light fragment, and also moving slightly up in average neutron multiplicity. And then over here is a measurement from several years ago from plutonium-240 spontaneous fission, where different energy thresholds were applied up from 0.4 MeV all the way up to 2.7 MeV. And you can see how it gets, the correlation gets steeper and steeper as you go up in those energies. And the nice thing about these neutron-neutron and neutron light fragment correlations is that they're very sensitive to the excitation energy division between the light and heavy fragments, and so depending on how you do that excitation energy split, the shape of the distribution changes. So we were able to get some idea about the excitation energy split in plutonium-240, where there was not a measurement of the neutron multiplicity as a function of fragment mass, just by looking at these neutron-neutron angular correlations. Okay, so now I want to talk about, I know I'm getting close to running out of time, but I want to mention something that's come up recently about the generation of fragment angular momentum. And I don't know how much Jörn talked about this on Wednesday, because I was traveling, and so I wasn't able to attend the talk. But recently there was a measurement of fragment spin in several systems by Wilson et al. It was published in Nature, and you can see it's kind of reminiscent of a sawtooth pattern, because you see the spin going up to some extent in the light fragment, and again going up in the heavy fragment, but in the region where there's no data, there's definitely a dip. So you can say, well, there may be some kind of sawtooth pattern. One thing that's kind of unfortunate is that these aren't actually fragment pairs that were measured. I tried to find pairs of fragments, and I could only find, I think, one in uranium-238 and californium-252. So it really doesn't say much about the fragment pairs, but it also, but they did manage. Sorry, my phone is gonna. Okay, I think it should stop now. Apologies for that. Okay, so they found little correlation between the fragment spins based on what they knew from their measurement. They were measuring photon lines, not so they could say that was how they could determine the spin, but also they didn't have any other correlation with the say with neutrons or anything. But because they determined little correlation between the fragment spins, they viewed this as evidence that the angular momentum could only be generated in the fragments after scission, so after they had separated, which doesn't really make a lot of sense, because they would have to abandon angular momentum conservation. I mean, they could say, oh, it's all taken up by the orbital angular momentum, but that there has to be contact for that to happen, for there to be transfer. Um, and they also claim that the sawtooth-like shape of the spin as a function of fragment mass was supposed to be due to the independent generation of fragment spin. Now we can actually test this with Freya because we can we have angular momentum conservation, so we can see if this makes any sense or not. And it's Freya is actually fairly ideal for studying spin effects in fission because of that. Um, so it can tell you something about the influence of angular momentum in fission. And we've studied this for in several papers now over the last few years, and we showed that we can show that the two fragment spins are nearly uncorrelated, even though they start out um, correlated. And so the fragment spins get determined at fission through something called the nucleon transfer mechanism. So nucleons get moved back and forth between, so the protons and neutrons are moving back and forth between the two protofragments through the neck until it breaks. And that there's this fission axis that's shown here. So there's a rigid rotation of both fragments around this axis, and that gives some an overall angular momentum to the system, and you can determine how much the light fragment and the heavy fragment get in spin based on the initial spin that's generated by the neutron coming in and starting the excitation process. And the amount of spin gets determined by the angular momentum and moment of inertia, these I's, and then the relative motion is the orbital angular momentum. So conservation tells us that the SL, SH, and L have to add up to the initial spin. But there are fluctuations, and here these are the rotational modes. I mentioned this rigid rotation already, and there's wriggling modes that where they're moving and rotating opposite to each other, and then the bending modes where they're going in the same direction, like, and then there's what's tilting or twisting, which is just going around the rigid rotation axis. And so these first two, wriggling and bending, are transverse. These are more longitudinal, and since their relaxation time is longer, we're actually ignoring those. So we rely on the fluctuations through the wriggling and the bending modes, and because the relative moment of inertia is generally bigger than the moments of inertia of the light and heavy fragments, then those dominate. And so even though you start off with these spins really based on the total, then you have these modifications that still conserve angular momentum, because whatever you add to the light and heavy fragment through these wriggling and bending modes, you take away from the orbital angular momentum. And then the rotational energy is based on all of these. This is the average, but then the total is this average plus the fluctuations, and the fragment spins, and so they're actually ultimately dominated by these fluctuations. And therefore, even though you might think that they're going to be very correlated because of this rigid rotation, in the end, because of the wriggling and the bending modes, then they're not very correlated at all. So this recoil from the wriggling will create some orbital motion, but the this the direction of the relative fragment motion gets redirected only by about 2 degrees, so that's not very much. And we found out that this is very, so this is the opening angle between the light and heavy fragments spins, and it's very independent of the initial energy of the neutron. And there's a slight preference for opposite spin directions, but it's not much. I mean, this is the scale here is from 0.9 to 1.1, so it's not a very big modulation. But we also can see that there's dynamical anisotropy that is produced because the neutrons get emitted from a rotating fragment, and that gives you an equatorial bulge in the angular distribution due to this centrifugal force. And so this is the angle between the neutron and this spin of the fragment. And you can express this anisotropy based on the distribution at 90 degrees and 0 degrees, and this is very small, about 0.1. So that changes the spin magnitude very little, less than 0.1 h bar, but it can reorient the spins by about 13 degrees. And this was published earlier this year in PhysRevC. In response to the Nature paper, we looked at, we wrote another paper that I just did the proofs for, and that's going to be out in PRL in the next week or so, probably, where we reiterated how you can get this almost no correlation between the fragment spins without resorting to letting the angular momentum be generated post-scission. But we also looked at the moments of inertia and how they may affect this spin as a function of fragment mass. And what we had been doing in Frye was just to take a smooth, simple mass-dependent moment of inertia, not taking into account any deformation, because when the deformation is based on the ground state shape, but when the fragments are initially generated, they may be very different from the ground state shapes. So as a default, we took this value, simple mass dependence, and there's a blue curve and a green curve here, and the green curve is supposed to show the difference in the spin after neutron emission, which is nothing really. But we also tried one other thing, fairly schematically, that takes into account the nuclear structure, at least in terms of the moments of inertia of the fragments. And so we made a very schematic estimate of how the moments, basically taking the ground state moments of inertia, and then using the creating mass dependence based on that. And then we saw, hey, this looks kind of sawtooth shaped, just like the data seemed to imply. I mean, it's not perfect, and we weren't trying to fit the data. We just wanted to show that if you took into account the structure related to the moments of inertia, then you would get a something mass is spin as a function of fragment mass that resembles the data, at least to some extent. It's much better here on the heavy fragment side. But we do get some kind of a sawtooth-like S of A following the behavior of the moments of inertia. And you can see that very plainly if you compare the red points to the dashed curve, which is basically scaling down the moment of inertia, so that it's on the same plot here. And so that brings me to my last slide, Um, so at least to summarize this part, we showed that there was a weak correlation between the fragment spins, even though they start out correlated. And we confirmed that there's a dynamical anisotropy due to neutron emission from the spinning fragments, but there's no strong dependence on the initial spin, and that the shape of S of A can arise from the deformation of the fragments. So, thank you for your kind attention, and if you have any questions, please ask.
Hi, Ramona, thank you very much for the presentation. And so we already have some questions in the chat, some that were asked during the presentation. The first one I think is something that you can answer now, which is can fission happen without the emission of any neutrons?
Sure. It would be, not very excited nuclei, but one plot I didn't show was the probability distribution for neutron emission, and to the neutron, or called the neutron multiplicity distribution, P of nu, and there's always some zero probability, but it's pretty small.
Yeah, so the answer is definitely yes. The second part is, were all the plots acquired using Freya? If yes, does it use libraries to get the data, or it simulates them using random methods like Monte Carlo?
So Freya is a Monte Carlo for sure. So so these plots are all and these slides, these are all from recent publications. In fact, this one isn't even out yet, but except on arXiv. This is data. So here, some of those are data and some are Freya. It's hard to see the difference on the scale, but the open points are Freya and the full are the data. Here there's data, Freya and CGMF, which is another code I mentioned. The lines here are all Freya calculations. This calculation, no data. There's no Freya calculation on here. This is just data. And this is all data. So these are kind of things we use as input. And we make some approximation of the energy dependence of the fragment mass yields as a function of energy, and also the TKE, which actually doesn't change very much in shape with energy. And using that initial information, we get like I mentioned, the total excitation energy, and then we divide it up, and we can then calculate things like these quantities shown here, and also the correlations. The data that we use generally is like the mass tables, or calculation of the masses if there's no data. Have a model for the level density parameter. We use ripple decay tables to for the discrete transitions, and so on.
So I think the person was interested in what you explained, that like what is the inputs and how much of it is calculated from the inputs. Because I think there is a variation on different codes will rely more or less on data. Like some codes will just take the data and just reproduce that exactly. Instead, maybe Freya is more starts with kinetic energy and masses.
Yeah, Freya is a Monte Carlo, so the yields are sampled. Okay, so we sample one. Here we go again. So we'll sample from a distribution like this, the mass and the charge, and the charge is from a different distribution, typically something like the unchanged charge, and then so it's a little bit more crude there for sure, but from sampling, say, the mass and charge for one nucleus, then like I said, we know the other from mass and charge conservation, and then we sample from the total kinetic energy, and this is basically um, how Freya, CGMF, and Fifrelin handle the initial input. GEF uses some kind of empirical model to get the fragment mass and charge, and then they have a model of the total excitation energy. So they don't use the measured total kinetic energy. Instead, they can extract the total kinetic energy based on their mass model and the total excitation energy. So they do it somewhat differently. So like in one of our papers, we used in calculations of stellar abundances in the R process. Freya was used to run through GEF yields, all the GEF yields for that was relevant for the R process, and to see how much difference there was in the neutron emission from the two codes using the same mass and TKE, and there was some significant difference, but it didn't change the the stellar abundances more than say 10% or 20% at the most.
Right. One other question is related to neutron-induced fission. Is okay. So what is the initial distribution of the total angular momentum of the compound nucleus, I assume here, for Newton-induced fission? So like how does what is how do you sample that? Because I'm assuming it's a distribution. So
yeah, I mean it's basically Gaussian based on the impact parameter. So when the neutron comes in, depending on where it hits the nucleus, it can generate more or less angular momentum. If it hits on the edge, it'll generate more than if it hits straight down the middle. But we can calculate based on the neutron's incident energy, and basically how much excitation energy there would be in the compound, and then from that we get the maximum spin that it could have, and then sample from that with a Gaussian around that spin.
And this so a classical approach.
Yeah, pretty much. And basically there are a couple of papers out now. One that's in PhysRev Letters, and one that's going to be in Physical Review C Letters, that we're looking at spin distributions for a given fragment based on this quantum mechanical many-body approach that I mentioned. And they're that's not so far off from the classical either. I mean, they claim they do it in what they claim is a more fancy way, but in the end it's fairly similar. And we actually took some of those spin distributions for a given fragment and ran them through Freya to see what the difference was in the photon emission.
So I don't see any more questions, but maybe I can ask a last one. And so my question is, I think you use the like words, like, I don't know, just you, but I think in the literature a lot, like people use spin and angular momentum of the fission fragments kind of interchangeably, like you can
Yeah.
say. So I was wondering, like, is there a, spin is more like the intrinsic properties and angular momentum would be more like the orbital motion of the nucleus. Is there like a way to model this in a Fry, or is that something that there is interest? Or, what is the status of dividing the spin into these two components?
Yeah, I mean, they're kind of used interchangeably. I mean, that's so like here, this L is, I would say that more what you would say orbital or relative, but it's not intrinsic to either fragment. It's just of the two of the system itself. So between the moments of inertia of the two fragments, you have the moment of inertia of the system, which is bigger here, and that's so yeah, the relative just depends on the total mass and this difference in the radii. And here, this is the general mass dependent moment of inertia. It has nothing to do with the deformation. In this point, this is what's there as the default. So I mean, the fluctuations have much higher angular momentum than just the relative. Just from either one, and the relative moment of inertia is going to be bigger than that of the individual fragments. And so, like I said, that's why you get the dominance of the fluctuations. But yeah, I mean, you can call it spin, but it's really the angular momentum of say one fragment, this SL, for example, and then SH is the same for the other one. Right, sorry, this is the L, that's the H, sorry. But then there's the relative motion, and this is just the R cross P. So, I mean, this I think generally works pretty well. But I wouldn't say that. I mean, I think you might get a clearer answer out of Bjorn, because he's studied this a lot more. I mean, he basically came up with his nucleon transfer model.
Right. Thank you. That was interesting. I think there are no more questions, and it looks like yep, there is that's our time. So yeah. Let's see. Thank you very much, Ramona. I'm gonna now stop the recording.